In this video, we're going to solve one integer linear programming practice question, question number 1 from chapter 12. So I have the question here. This question is about a paper mill company, and what they actually do is that they get wide and large paper rolls, and they cut it in smaller rolls of width. Actually, they get it in 100 feet wide rolls, and they cut it in 12, 15, and 30 feet wide rolls. So we're assuming in this question that they can only do it in either of these 5 patterns. And so, for example, in pattern 1, they're given, if you assume 100 feet wide paper roll, if they cut it in only 15 feet pieces, they're going to end up with 6 15 feet rolls. And at the end, there's going to be 10 feet of trim loss that is not going to be useful because it's less than 12, which is the smallest size of their paper rolls that they can sell in the market, right? Just to visualize how these patterns work, let's just take a look here. So assume, let's take this one, these large bar as a, their input, which is 100 feet roll. So assume each one of these cells, each one of these small cells to be 1 feet. So this would be the original 100 feet wide roll. And they can cut it in different patterns. We just talked about 5 different patterns. These are the patterns that the question provides. So the first pattern, I said they just cut it in 15 feet rolls. So this is the first 15 rolls. They just make a cut over here, and then they make another cut over here. They make another cut over here. So far, 15 feet rolls, another cut over here, another cut over here, another cut over here. And after they make this cut, there's going to be 10 feet left, but 10 feet is going to be trim loss. It's going to be waste because they won't be able to sell it in the market, right? So this will be considered as waste, as trim loss. The second pattern, if you only, so let me just go back to the question here. The second pattern, there's no 12 feet, no 15 feet, only 30 feet, 30 feet rolls, right? And then there's going to be 10 feet of trim loss. So again, 130, they just make a cut over here, another cut over here, another cut over here, and there's going to be 10 unused, 10 trim loss. Next pattern, 12 feet, only 12 feet rolls. A cut over here, another cut over here, another cut here, and so on until you get to here. And then there's going to be 4 feet of trim loss. Next one is a blend of 12, 15, and 30. So 212, a cut here, another cut here. So there's going to be 212, another cut over here, 115, and then 230. One over here, one cut over here, and another cut over here. And there's going to be 1 feet left, 1 foot of actually trim loss. And then again, the last pattern is also a blend of 12 and 15. You go with, I think 7, 12, and 1, 15. And then there's going to be 1 foot of trim loss. We have the demand in this question. The demand for 12 feet is going to be 5,670, 1,680 for 15 feet rolls, and then 3,350 for 30 feet rolls, right? So we want to formulate this problem in order to as an ILP problem, in order to find the best cutting pattern, the best way that we can use these 5 cutting patterns in order to meet the demand. And also our objective is going to be to minimize the trim loss. So we want to meet the demand with the least amount of trim loss, with the least amount of waste, right? So here's the decision. I'm just going to write down the formulation and then we go ahead and solve it. Decisions that we have to make, or decision variables, are going to be the number of 100 feet wide rolls that are going to be cut using each pattern, using pattern 1. So that's going to be x1, decision variable 1, the number of original rolls, large rolls that are going to be cut using pattern 1. So that's how I define my decision variables, number of 100 feet wide rolls to be cut using pattern I. Pattern I, and I call this xi, where I can be 1, 2, 3, 4, and 5. All right. So that's my decision variables. I have 5 decisions to make. How many rolls, how many of large rolls to be cut using pattern 1, using pattern 2, pattern 3, pattern 4, pattern 5. So 5 decisions to make. And then objective function. This is actually given to us in this question. So it says here we want to minimize the trim loss. And trim loss is going to be, so let's say we are cutting x1 unit of large rolls using pattern 1. So for each, if I go back here, for each 100 feet wide roll that you cut using pattern 1, there's going to be 10 feet of trim loss. But now if you use x1 units of these big rolls, there's going to be 10 times x1 of trim loss, only for pattern 1. If you use, if you use pattern 2, there's going to be 10 feet of trim loss per 1 large roll that you cut. Now, if you use this pattern on x2 rolls, there's going to be 10 times x2 feet of trim loss, right? So I'm just going to write it this way, 10 times trim loss per pattern 1, but I'm using it on x1 units of large rolls, plus 10 times x2, plus 4 times x3, plus 1 times x4, plus, we don't need to type 1, and x5, 1 times x5, right? So that's what we want to minimize. But then we have some demand to meet. We want to meet the demands for each one of these smaller rows. So for 12 rows, so constraints are subject to demand constraints. Subject to the demand constraints, and then I'm gonna write it for 12 feet, 15, and 30. Okay, so for 12, the amount that we produce of 12 feet, 12 foot roll should be at least equal to this number. Should be greater than or equal to this number, which is our demand, right? So we want to meet the demand. So the total number of 12 feeds that are produced, if we only use pattern 1, no 12 feed is 12 feed roll is produced. If we use pattern 2, again, no 12 foot roll is produced. If we use pattern 3, 8 of these 12 foot rolls are produced. So it's going to be the 8 times x 3. So per each roll that you use pattern 3 to cut, there's going to be 8 12 feet roll to be produced. Now, if you use this pattern on x3 rolls, x3 large roll, there's going to be 8 times x3 plus 2 times x4 plus 7 times x5. So this is the total number of 12 foot roll that you can produce. And this has to be greater than or equal to 5670, which is your demand for 12 foot rolls. For 15 foot rolls, you have, if you use pattern 1, you will end up with 6. So that's great. 6 times x1. Pattern 2, nothing. Pattern 3, nothing. Pattern 4, 1. So 1 times x4 plus 1 times x5. This has to be greater than or equal to 1680. For 30 foot rolls, pattern 1, if you cut using pattern 1, no 30 feet. For using pattern 2, each one of that is going to end up with 3 30 foot rolls. So 3 times x2 plus nothing with pattern 3, 2 with pattern 4, 2 times x4. And so this is the total number of 30 foot rolls that you can produce with these decisions that you're making. And that has to be greater than or equal to 3350, which is your demand for 30 foot rolls. All right. And that's really about it. The only thing that is left is that you need to make sure that xi's should be greater than or equal to 0 and also integer. We can't use a fractional amount for actually rolls for the number of 100 feet wide rolls that we caught using each pattern. So that cannot be a decimal number, right? So this is our formulation. Now, let's go ahead and solve it in Excel. So that was our formulation, mathematical formulation. Now I'm going to model it in spreadsheet in Excel, and then we're going to use Excel solver to solve it. So pattern 1, 2, 3, 4, and 5. So this will be number of 100 feet or 100 foot rolls to be cut using each pattern. So that's my decision variables. I need 5 of them. So 5 decision variables. And all right, decision variables. The objective function, DVs. That's the decision variables, and then objective function. The trim loss, it's going to be, if I had the trim loss as you know what, let's just do it. Let's just first write down the set of the parameters, and then we're going to use those to I'm going to use some product function that'll make it a little faster. So 12 feet, 15, and 30, and then trim loss 00827 60011. 30 feet is going to be 03020, and trim loss is going to be 1010,411. Right? You don't have to put zeros, but just put them here. Okay. So these are the set of parameters. Now, objective function, the trim loss is going to be sum product of the trim loss per each pattern multiplied by the number of rows, large rows to be cut using each pattern. So that is my objective function. All right. And now we have the demand to satisfy for these three. Just put it here. So demand. So this is the production should be greater than or equal to the demand. And you know what? It's actually better if I just do it the other way around. So I just Control C, maybe put it here, transpose, yeah. And then get rid of this. Sorry, I think since I put 12, 15, and 30 this way, horizontal, it's probably better to write down them horizontally. That way I can, again, use the sum product function. So for 12 feet, the left-hand side is going to be the sum product of these values and the decision variables. Right? 8 times x3 plus 2 times x4 plus 7 times x5. That has to be greater than or equal to the demand for 12 feet, which is 5670. 5670, and then for, let me just write down the right hand side for 15. 15 was 1680, and 3350 for 30 feet. So what I can do here is fixing in my formula, fixing the decision variables. So L20 to L24, if I just press F4 and add the $sign, they're going to be fixed in my formula. That means I can go ahead and drag my formula to the right. So I don't need to type it again. So let's say for 30 feet, it's going to be 30 feet, the number of patterns, sorry, the number of 30 feet rows in each pattern multiplied by the number of 100 foot rolls to be cut using each pattern, right? That has to be greater than or equal to 3350 50. So these are parameters, decision variables, objective function that contains the formula here, or I can just put the formula right here, objective function, and then three constraints, one for each size of paper rolls for 12 feet, 15, and 30. And I can, like I said, I just type the formula, I fix the decision variables in my formula by pressing F4, and then I was able to drag my formula to the right. Right, so the formula, let's say for 30 feet, is the sum product of these values and the decision variables, and that has to be greater than or equal to the demand, the minimum demand that we have to satisfy. So our spreadsheet model is ready. We can go ahead and go to the solver and solve it. As we have to set it up first. So we want to minimize, make sure to check minimize what? The trim loss by changing the decision variables subject to three constraints. So these are the ones. I have to have my production greater than or equal to the demand for each size of the paper rolls, right? Okay. And then there's one more thing. I have to change the solving method to simplex LP. There's one more thing. We just here, the way we defined, we said the xi's cannot be negative, plus they have to be integer. So I'm going to add another constraint, and I'm going to define all these 5 decision variables to be integer, to take integer values. So I'm going to enforce that as a constraint here. So, okay. So all is good. Our setup is now ready. We can go ahead and solve it. So when we solve it, so solver found a solution, an optimal solution, a feasible optimal solution. And as you can see here, there's no sensitivity report. You can ask for the answer report. It just lists the actually list of decision variables, and it's going to outline the values that each will take. But I'm just going to look at it from my spreadsheet model here. So the minimum trim loss that you can have for making sure that you're satisfying the demand is going to be 1,680 feet of trim loss, and you're only using the blend patterns, not just the ones that only use one type, one size, right? So you're using a lot of pattern 4, which uses all sizes, and some of pattern 5. And then you are satisfying the demand, right? You're satisfying the demand of each size, basically. The amount of production is always greater than or equal to the demand.